How's everybody doing? Professor Bryant back with another installment of tutorials via light atom technology. Today, we are going to be looking at electronic configuration, general electronic configuration, also noble gas configuration, and talking about how we properly write these configurations that express what energy level the electrons are in and what subshell they're in, or what type of orbital they are in. So what you see here is a diagram, which I call an orbital energy diagram, showing that the increase of energy is a function of principal energy level, which N is equal to 1, 2, 3, etc. And also a function of what we remember from our quantum numbers, the angular momentum quantum number, or the shape of the orbital. And we see those as, we recognize that they are numerically listed in quantum numbers, but they correspond to S, P, D, and in fact S. Remember, we add electrons from lowest to highest energy. We also add electrons in one box before we pair them. And we also only pair electrons with opposite spins. So that is a combination of the Pauli exclusion principle, the Aufbau principle, and Hund's rule. All three of them kind of woven into one instructional statement. Lowest to highest energy, place one electron in each particular orbital within a subshell first before you pair them, and when you pair them, they must have opposite spins. So let's go through a couple examples. If we look at gallium and we go to our periodic table, which you should always have handy, gallium is going to be shown to be in group 3, okay, which is the group that starts with boron, and it is in group 3. It is also in period 4, which means that the highest energy electron you would expect to be in the 4th principal energy level. It's also located in what I call the P block, which is the right-hand side of the periodic table, starting at group 3, or what is generically called group 3. So gallium here has a total of 31 electrons. How do we know that? Well, its atomic number is in fact 31. So we should expect 31 total electrons. Now, if we were to utilize our orbital energy diagram to show those 31 electrons, we would see that there will be 1, 2, 3, 4. And I'm going to fill this as it should be filled. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Notice that we have now represented these electrons on our orbital energy diagram. However, when talking electronic configuration, there is a way to represent this that involves only the principal energy level, the orbital or the angular momentum, which is the shape of the orbital, which we denote by a letter using those S, P, D, and F in electron configuration, and a superscript showing us the total number of electrons. So what does that look like here? It looks like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. And we have now taken care of all of the electrons shown. The only thing that the electronic configuration in general does not show are the spins of the electron, which we do the spin and the magnetic quantum number, or which orientation of an orbital the electron is in. But remember, these orbitals, as we see them here, are considered degenerate. And because they are degenerate, they are all of the same energy. So electronic configuration kind of simplifies that for us. Now, if we want to talk about the noble gas electronic configuration, then we recognize that our noble gas stops. I'll use a different color here. It stops at 3p6. Therefore, we can technically use argon, 4s2, 3d10, 4p1. And we have two valid electron configurations for gallium. Now would be a good time for you to pause the video, try your hand at krypton, Kr, and rhodium, or H, and verify that you can, one, fill out this electron energy diagram and be able to write the regular and noble gas electron configuration for each of those elements. Now I'm going to go ahead and move forward and try to erase these, and let's work on those other two as well. I'm going to rewrite some of our lines for 4p and 3d. Okay, so if we were looking at krypton and we went to our periodic table, we see krypton is in the fourth period as well. It is in group 8, the noble gas group. So looking at its atomic number, we see it is 36. That means we should expect 36 electrons. And if we fill this in appropriately, we would have all of our energy levels full. And I'm going to just make a shortcut here. But remember, these are filled one at a time and then paired with opposite spins. But since all energy levels in this atom that house an electron are full, krypton is full for every single box or every single orbital shape that exists. Because of that, we then realize that this is going to be a very similar electronic configuration to gallium above us, except we should have 6 electrons in the 4p. I should highlight for most students that this is the mistake that most students are going to make, or the misstep that could potentially happen. Remember that 3D occurs after 4s in a given electron configuration, meaning that you do not write 3p6 3d10. You write 4s2, you write then 3d10, because the electrons are placed in d orbitals, but those d orbitals exist in the third principal energy level. And we learned that from experimentation with atoms that have d electrons. Okay, moving forward. If we take a look at rhodium on the periodic table, we see that rhodium is in the 5th period in the D block. And what does that mean for us? So 5th period in the D block means that we should expect to have more electrons than each of the examples that we have shown previously. So if we go for P, we should now have 5s, and then for D, which I'm going to have to add to our orbital energy diagram as shown here. Okay. We should also take a look at rhodium's atomic number, which in this case happens to be 45. So we should have 45 total electrons listed in our electronic configuration. Now, I'm not going to fill all of these in. Recognize that they all needed to be filled in, but we have now moved to 5s, and rhodium has, looks like 7d electrons. So if we fill those in using our rules and principles, we would fill them in one at a time, 5, and then we would have 2 of them paired. Okay? This is the correct way. And make sure that you are writing these that are unfilled in the d orbital that have multiple orientations of atomic orbitals where the electrons can reside. Make sure that you do not have 3 pairs in one single electron, because that's a mistake that many students will make in this situation. Now, given that, we now have a little bit longer of an electronic configuration, but notice that the pattern stays the same. 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d7. Okay? Now, you should try your hand at the noble gas configuration for krypton. It can be written a couple different ways, and the noble gas configuration for rhodium. I will now utilize 1 electron in rhodium to utilize for studying quantum numbers. Just as a quick review, remember that quantum numbers, let's say we wanted to pick the last electron entered into rhodium, which would be that 7th d electron here. And to give the quantum numbers for that, as a quick review, we should recognize that n is equal to 4 because it is in the 4th principal energy level. L, because of the type of electron, is equal to 2. It is a d electron. M sub L is -1 because of its placement. We should remember a -2, -1, 0, 1, 2. And then because it is the 2nd electron to go in, convention states that it should be at -1/2. So this is your quantum numbers as a quick review. But this should explain to you proper electron configuration. I gave you examples in and outside of the D block, as well as the orbital energy diagram to show how these are arranged, generically speaking, in energy. And if you have any questions, feel free to send me an email. See you later.